For many years, carbon dioxide has been employed as a solvent in the extraction of natural materials and the cleaning of precision components, such as semiconductor wafers. Core Separations integrates numerous precision components to create a system that utilizes carbon dioxide effectively as a supercritical fluid in these processes. This procedure begins with the condenser. The condenser is a tube-in-shell heat exchanger and is designed to guarantee that the carbon dioxide maintains its liquid state upon reaching the pump. It is cooled through a recirculating chiller and typically operates between 4 and -5 degrees Celsius. Once the carbon dioxide is cooled, it passes through a Coriolis flow meter that measures its temperature, density, and flow rate. The flow meter, paired with the pump, facilitates precise control of the CO2 flow rate to the extraction vessel. On reaching the pump, the carbon dioxide undergoes compression. Modern systems commonly compress liquid CO2 to the elevated pressures required for processing. Compressing a liquid is notably more efficient than compressing a gas because liquid compression necessitates only a single stage, whereas gas compression may require 2 or 3 stages to attain the requisite high pressure. The pump, featuring a 2-headed piston design, incorporates cooling for the heads to dissipate the heat generated during compression. While carbon dioxide is versatile in extracting a wide variety of natural products, there are occasions when introducing small amounts of solvent is necessary to aid the extraction of more polar compounds. The Co-Solvent Pump can deliver a diverse range of solvents to adjust the carbon dioxide for more polar extractions and can also be utilized for in-process cleaning at the conclusion of the run. The sole function of the pump is to produce high-pressure liquid carbon dioxide, not to transform it into a supercritical fluid. This conversion is achieved by channeling the CO2 through another heat exchanger. It is this heating that generates the supercritical fluid. This step also ensures it's at the necessary temperature before it enters the extraction vessel, guaranteeing a stabilization of the extraction conditions. The extraction vessel, where the biomass is placed, typically holds it in the form of a milled powder, secured at both ends of the vessel using 5-micron filters. The vessel is heated to precisely control the carbon dioxide conditions. A tightly packed vessel is pivotal to ensure the carbon dioxide is directed through the bed, facilitating an efficient extraction. The back pressure regulator assists in generating the necessary pressure within the extraction vessel. The needle within the regulator closes until the desired pressure is attained. It is this restriction combined with the CO2 flow rate that generates the pressure inside the extractor, while allowing carbon dioxide to traverse, enabling material collection. The system monitors the pressure and makes corresponding adjustments to the needle position. A pressure drop is typically necessary to influence the solubility of compounds in the carbon dioxide stream. However, this drop in pressure triggers the Joule-Thomson effect, which effectively cools the CO2. This cooling process can result in a liquid carbon dioxide stream, dissolving substances and preventing collection. Alternatively, it can freeze any existing water, which could potentially lead to a blockage. The vaporizer warms the CO2 to counterbalance the temperature decrease caused by the Joule-Thomson effect. The separators are the point where the extracted material arrives. They are heated to keep the carbon dioxide at the appropriate conditions for separation. Systems that utilize multiple separators can establish a density gradient, aiding in the separation of different classes of compounds. During an extraction, it is common for the more soluble compounds to be collected in the final separator. Compounds such as terpenes can be highly volatile, so to assist in their retention, the last separator is cooled, functioning as a cold trap to retain the more volatile components. Finally, the manual pressure regulators control the pressure within the separators. Similar to the automatic version on the extraction side, the manual regulators manage the pressure inside the separators to establish an environment conducive to collecting the extracted material.